Hello everyone, so let's continue with our topic. We have studied in our last lecture with about plane of symmetry, right? So guys, I think everyone must have understood. So I think, are you enjoying or not? Okay, so enjoying. Okay, so let's continue. So plane of symmetry is covered already. Let's start with center of symmetry. Okay, it is also called as center of inversion, represented by Ci. So first of all, let's understand what is the meaning of center of symmetry. Okay, I am giving you with a very small and very simple example of benzene. See, this is benzene. Okay, what happens here? You have to choose one imaginary point. Okay, select one imaginary point. Now it does not matter that point is the center of the molecule, center of the axis, center of any bond. It is an imaginary point which can be chosen in any part of the molecule or outside of the molecule, no problem. Okay, now after choosing the point, when you draw a line in such a way, if you get one atom or group in one direction in a particular distance, and if we get the same atom or group in the opposite side in same distance, then it will be having center of symmetry. But in this case, you have to remember that it must be valid for each and every atom of the molecule. Each and every atom of the molecule means, let's see the perfect structure of benzene and understand. See, all the hydrogen atoms here are sp2 hybridized, right? Means it is planar. So this molecule is your benzene C6H6. Now I am taking this center point. Okay, now first understand center of symmetry with this example, then I'll carry out the definition part. From this center point, if I draw a line in this way, suppose this line, okay, so you can see if I move this much distance in this line, this side, I get hydrogen atom here. Again, opposite side, equal distance, I get hydrogen atom here. Okay, in this much distance, carbon atom, again this much distance, carbon atom. Again, if I see this side, same this much distance, hydrogen, opposite hydrogen. From this side, from this side. So I can simply say benzene is having center of symmetry. Why? Because on choosing an imaginary point, if I draw a line and on moving from one side, if I get some atom or group towards a line, then on moving in opposite direction, I am getting the same atom or group on equal distance. Then it is having center of symmetry. Okay, let's take another example. Boron trifluoride. So if I see the center, suppose this point, then if I move this side fluorine, this side is nothing, this side fluorine, this side is nothing, you have nothing here, you have nothing here. If I move this side fluorine, this side is nothing, so you cannot say COS present, COS absent here, but here COS present. Again, if I say water, okay, lone pair. So as you know, it is having POS, divide like this, or in the molecular plane containing oxygen, hydrogen and hydrogen, POS is present, but COS is absent. Why? Because if you choose any of the center, if you move, this is V-shaped, as you know, V-shaped, right, or bent. So this side, if you choose this side, then opposite side will not be hydrogen, OH bond. Okay, so it is not having COS. It is also not having COS. If I choose example of NH3, lone pair this side, H, H and H. See, it is having POS, but COS is absent. Why? Because if I go this side, lone pair, so this opposite side, no lone pair. Clear? So let's note down the definition of COS. Center of symmetry. Okay, imaginary point is chosen in any plane such that a line is drawn from that point on moving both sides. If we get same atoms or groups on equal distance, then it have center of symmetry. Okay, now also if a molecule is having center of symmetry, if compound have center of symmetry, it must be achiral. Achiral means symmetrical, means optically inactive. Okay, optically inactive means it will not show any optical activity. So guys, let me explain. Imaginary point is chosen in any plane for the molecule such that a line is drawn from that point. So this was our benzene. Imaginary point is chosen, any point can be chosen. So this point, you have drawn this line, okay, on moving both sides, on moving this side and this side. If we get same atoms or groups on equal distance, here you have hydrogen, here you have hydrogen, then it have COS. If compound is having COS, it must be achiral or symmetrical, means optically inactive. Now again, remember this point. We will discuss in examples, but here I am just writing Fisher projection can't explain COS perfectly. Means I will show you by the example what happens in Fisher projection. We cannot perfectly observe the center of symmetry. So we have to observe that Fisher projection where vertical line and horizontal lines are there in 3 dimension. So you can clearly imagine, right? Okay. So let's take some examples. Let's see this ring. Now what happens? If you will say that sir, let's see this point, okay, on moving this side chlorine is there, on moving this side chlorine is there, on moving this side you have hydrogen, on moving this side we have hydrogen. But then now someone will be thinking, sir, is this the midpoint? How can you say this is the midpoint? Okay, you choose any of the point carrying this plane, any point such that this distance and this distance is equal. So this side and this side equal, Cl Cl, hydrogen hydrogen. But the question arises, what about this carbon? If we move this side, it is carbon. If we move this side, there is nothing. So guys, understand, it must be observed for all the atoms. Okay, so here you cannot say it is having COS. Clear? Now let's take another example. Okay. Okay, let's observe this example. What about symmetry, center of symmetry in this molecule? So if I choose this part as the center, so I can see here it is having carbon, it is having carbon. From here, if I come this side, I get methyl this side, I get hydrogen this side, I get hydrogen this side. Okay, so I can surely say it is having center of symmetry. But see, you can also observe here that this methyl and this methyl are opposite side to each other. So it is your trans form. Okay, so let's check if the cis form of this molecule, what will happen? If this methyl was upside, this methyl is also upside. Now what will happen? So if I will select the midpoint, what will happen? This side is methyl, so this side must be methyl, but it is hydrogen and methyl, so COS is absent. Okay, clear to you? Third example. Let's come to fourth example. Now, just think whether it is having center of symmetry or not. From this point, this side is deuterium, so this side is deuterium. This side is chlorine, so this side is chlorine. And if I come this side is bromine, this side is also bromine. So guys, you can say it is having center of symmetry. Okay. Now suppose if I ask whether this molecule is having plane of symmetry or not. Okay, as we have already studied in our last video lecture, so you can answer it very easily. So let's see plane of symmetry in these cases. So using the molecular plane, if I say molecular plane, I can say it is having plane of symmetry. Plane of symmetry is present in this molecule. Okay, so as it is having POS as well as COS, so it is surely optically inactive. It will not show any phenomena with respect to plane polarized light. Now if I see this molecule, so you can cut this molecule using the imaginary plane which carries this atom and this atom. So it will cut this methyl and this methyl, this methyl and this methyl. So it is having your plane of symmetry. So as we know, if the compound is having plane of symmetry or center of symmetry or both, then it will be surely optically inactive. Now let's say this example. Now as we know, if I select a plane which carries these both carbons, so whether the methyl is upside and this is downside or both upside, it will not matter. It will be surely having plane of symmetry. Okay, so everyone have understood this thing, right? Let's continue with some more examples. Find center of symmetry in given compounds. Okay, so let's understand with these two examples. Okay, so if you will see, both the compounds are actually having different arrangement in space, remaining everything is same. Okay, so in this example, Cl are in front of each other, you can say. Why? Now see, one more thing, as I discussed in the definition part, in Fisher projection, if I have to observe this COS, then I cannot observe it perfectly. Now let's see here. In this, it is very clear. If I go this side, it is chlorine. If I go this side, this is hydrogen. So it is surely not having COS. Confirm. Done. This side is methyl, this side is methyl. This side is chlorine, this side is hydrogen. So it is not having COS. In simple terms, I am saying, using Fisher, I can also say it is not having COS. In the way you are observing. But as I know, it is having plane of symmetry. Right? Now let's observe this example. Here, if you will take the case of Fisher projection, what will happen? You will say that, sir, You can see here it is chlorine. You can see here it is also chlorine. You can see here hydrogen and here hydrogen. Here it is methyl. Here it is methyl. So if you will consider only Fisher part and won't imagine in 3 dimension, you will say that it is having COS, center of symmetry. But guys, if you observe it in 3 dimension, let me show you. As you know, this part is towards you, right? And you see this part is also towards you. As you know, in Fisher projection, this part is towards us. This part is also towards us. This is our wedge part, right? So now you understand this. Now you can understand it perfectly. If from this center I go this up to this chlorine, this distance and this distance, okay, but this chlorine is above the plane. See, this chlorine is above the plane, okay. So from this point up to this point, it is above. So if I move above this distance, so I must go backside to that much distance. But here you can see this is above this side and this is above this side. So it is not a line, okay, it is not in a single line. And I have told in the definition, using the point, imaginary point, you have to first draw the line, and on moving in the line in equal distance, you have to find the same atom, then it will be COS. But here, if I move in this line, so the back line will not carry this chlorine atom, so it is not having center of symmetry. Clear? Again, if I am asked whether it is having plane of symmetry, no, it is not having plane of symmetry. Plane of symmetry is also absent. Clear? Using this plane or this plane, you cannot say it is having plane of symmetry. I think it is clear to everyone. Okay. Find COS in given example. Now this is your methyl hydrogen, chlorine, H. This is your first example. Guys, everyone find in this question COS and POS. Okay, let's check how many of you are doing correct. Now in this one, methyl H. Now okay, so I think you must have covered this. Okay, so let's do one thing. If you have done the correct answers in both the cases, then in comment section you must write whether you are correct or not. Okay, so you can give yourself a score in the comment section of this video if you have done perfect in both the cases. See, the question was to find POS and COS in question number 1 and question number 2. If you are all the 4 answers, POS, COS here, POS, COS here, 4 question. If you have done all the 4 correct, then it is excellent. If you have done 3 cases, then it is best. If you have done 2 cases, then it is good. If you have done only 1 correct, then it is just okay. So, first check the answer, then give your comment. I will check it. Okay. So guys, let's see one by one. In this case, if I select this as a center, okay. Now, first of all, understand, as we have learnt in conformations, that 4-member ring is not exactly planar, but when we have to check plane of symmetry and center of symmetry, then you may imagine it in 3 dimension and you will consider it as a rigid form. There is no incorrectness in that. You can use that term rigid form in this case. Okay, so let's see what will happen. If I'll move this side upward, see chlorine is upside and this side is chlorine downside. So this is COS. Here also methyl downside and here methyl upside. So it is having COS present. Okay, so I think some people must be happy if their answer is correct. COS is present. Methyl downside, downside, and this chlorine upside and downside. Okay, so COS present. Now when I see plane of symmetry, okay, what will happen? If I'll select a plane which carries this carbon and this carbon, then it will not matter whether this chlorine is upside or downside. I can simply cut this. But if I'll observe this methyl is upside and this is downside, so there will be not mirror image part. Okay, using this imaginary plane, when I cut in two equal halves, so this part and this part are not mirror image of each other. So it is not having POS. Okay, so I think most of you have done correct, I think. Okay, good. So let's see this part. One was okay, right? One was okay. Two is good. Okay, so let's see this one. Now here what will happen? If I take this middle point as the imaginary point and I move this side, so here methyl is upside and here methyl is also upside. So COS is absent, no COS. Okay. So I think it's best if I've done all three correct. So these three methyl upside and downside, this methyl upside and this methyl also upside. So you cannot say COS here. But if you will observe this COS is upside and this CO is downside. Now many students must be having this dilemma that sir, whether to say this molecule is having COS or not, because with respect to chlorine atom, if I observe this chlorine is upside and this chlorine is downside, so in that way also this hydrogen is downside and this hydrogen is upside. So I may say that it is having COS with respect to chlorine. But see, as I have told with respect to definition, every atom must be equal. When we move, considering all the parts, it will be same, then it will be COS. So here with respect to this ClCl it is COS, but with respect to methyl it is not COS. So simply it is not having COS. Okay. Now plane of symmetry. Okay, so last part. If you have done it correct, you can comment yourself as excellent. It is having COS, POS. How? Using this carbon and this carbon in a plane. If I'll place a plane like this, you can see this methyl upside, this methyl upside. So it will be having mirror image part. Okay, so students, I think everyone must have done this in correct format. Okay, excellent. Okay, so friends, in these examples, you can easily check center of symmetry. Why you can easily check is, I have already discussed the same examples in plane of symmetry. So you understand whether this molecule is planar or not. You can understand how to check their hybridization. So in that way, let's see one by one. Okay, so if I have noted it, please do yourself first. Okay, then you have to match. Okay, right, same way. So in this case, if I check this point as a center, I can see this methyl and this is hydrogen, so it is not having COS. From a single part, I can say whether it is COS or not. Okay, because as we know that every part must relate, right? Also, if I see it is having one double bond, so it is planar. It is your cis form if you observe. Now, in second question, I have drawn the trans form. You can see it is actually cis 2 butene 1 2 3 4. It is your trans 2 butene, so it is trans. it was having POS, right? Molecular plane, or in this plane. Now in this case, if I cut from molecular plane, it is having POS. Okay, now check COS. From this, I can see methyl here, I can see methyl here, I can see hydrogen here, I can see hydrogen this side. Okay, so it is having center of symmetry as well. Clear? Okay, done. Now come to this point. Now what happens if you are unable to examine this pi bonds, cumulene structures? Then what will happen? You will simply say, sir, this carbon is having chlorine here and chlorine here, this hydrogen here and this hydrogen here, so it is having COS. But in reality, it is not having COS. Why it is not having COS? Because as you know that these both pi bonds are perpendicular to each other. So if this part is in the plane itself, but these two are, that chlorine is backside of the plane and this hydrogen is towards. Okay, so from this center, if I come in the plane chlorine, so it is not in this plane. Okay, so here COS is absent, right? Now see this example. What about center of symmetry in this example? So here, as we know, 3 pi bonds continue, right? So as we know, this is PZ, PZ, SP, SP, PZ, if you remember. So it is PX, PX. So it will also be PX. See, it is PY, PY, pi bond. So it is PX, PX. Now you can simply understand here, it is planar. So if I will say this chlorine this side and this side, from center equal distance, and here hydrogen in equal distance, so it is having center of symmetry, yes. It is also having plane of symmetry, yes. Okay, so I think I'll mark you excellent if you have done all the cases correctly. Let's see another case. Now here, if you will observe perfectly in these questions, what is the change which I have done? CuNH, CuNH, from this center, this part and this part is exactly same. This part and this part is exactly same. This part methyl and this part methyl is same, and hydrogen is same. So here COS is present. You can see here this methyl and this methyl, it is your trans form. Okay, now if you will observe here, it is your cis form. Now from this point, this methyl part will not be related as per your same line concept of COS. So COS is absent here. Okay guys, this is one of the very good example to observe COS. This is generally asked in competition examinations, this question. Okay, so let's continue with next part. Axis of symmetry. Now what is axis of symmetry? See, it is one of the type of symmetry which we will be studying definitely to understand the type of symmetry, but you have to understand that there is no relation between axis of symmetry and optical activity. Means a compound may or may not be having axis of symmetry. In that case, it may be optically active or inactive. Means if a compound is axis of symmetry, then you cannot say surely that it will be optically active or inactive with respect to axis of symmetry. It is not possible to say perfectly. Okay, but let's see what it says. If a molecule is rotated 360 degree by n equals to 1, 2, 3, any number, and we get same molecule, then it is having axis of symmetry. Okay, now if, see, there is no meaning to say n equals to 1, right? Remember this thing. So that will be simply 360. So if you rotate any molecule by 60 degree, you will surely get same molecule only. So if n equals to 2, 360 by n will give 360 by 2, that is 180 degree. That will be your C2. N equals to 3, 360 by 3, that is your 120 degree. That is your C3. N equals to 4, you get 360 by 4, that is your 90 degree. It is called C4. Similarly, if you say n equals to 6, it is your 360 by 6, that is your 60 degree. So that is your C6. Okay. See, I have told you these 4 cases because these are generally used and mentioned in various books and sources if you will search. C2, C3, C4 and C6. Okay, so let's see examples to understand this concept. Okay, I think everyone has noted, right? So let's see how to check axis of symmetry, right? Cn. Now we are telling, suppose I am having a compound 1. Okay, now using any axis of symmetry, any axis, suppose this one, rotating, suppose I am telling it is C2. When I say C2, it means 360 degree by 2, that is 180 degree rotation. If I get another compound, and if these two are identical, it means it is having AOS present. If not identical, then AOS is absent. Clear? So students, let's see from a few examples. First, now this is our benzene, right? Now if I take this axis and now if I rotate, see what are the possibilities. If I say C2, C2 means 180 degree rotation, 360 by 2, 180 degree. Then this part will be completely rotated. Then also we will get benzene same as it is. So C2 is possible. Now, if I say 120 degree rotation, C3, then this part will come 60, 120. Okay. Now in case of 120 degree, as we know, this is exactly very perfect hexagon type, right? And in the plane. So 120 degree also possible. Now if I say C6, 60 degree rotation, that is also possible. So we can say all these are possible cases. Okay. Now if I say a simple inorganic molecule to let you understand here about different types. In this molecule, let us suppose this axis is chosen. Okay. Now from this axis, if I just turn this molecule, means I am talking about C2, 360 by 2, that is 180 degree. So what will happen? This fluorine and this fluorine will be interchanged. This will be, here it is, this will be again as it is. So it will be having C2. Now one more possibility. See, these all the 3 bonds are equivalent, same bond length and 120 degree bond angle. So if I will rotate by 120, it will come this side, it will come this side and it will come this side. So C3 is also possible. Okay. So it is having C2 axis of symmetry as well as C3 axis of symmetry. Okay, dear students, done. See, let's take other example. Okay, now when I say in this molecule, what will happen? Suppose if I will rotate this molecule to 180 degree, means if I say this plane with C2, means what will happen? This will exactly rotate 180 degree. means this will come this side and this will come this side, 180 degree. Okay, simply I am telling that I will catch this side and I will turn it like this. Okay, so what will happen? This Cl will come here this side, this hydrogen will come this side, means it will be having C2. 180 degree rotation will give identical part. So it is having axis of symmetry. Okay, so dear students, from this you can understand that if we rotate any compound by 360 degree by n, where n equals to 2, 3, 4 and so on, integer values, right, starting from 2, then if we find the identical molecule, then we can say it is having axis of symmetry. But we need to understand that there is no relation between axis of symmetry with optical activity, right? Because it has been observed that a compound having axis of symmetry can be optically active, and a compound not having axis of symmetry is also optically active. Okay, so I think it is clear to you. So we have finished with POS, COS, AOS. Now it's time for AAOS, right? Let's continue. See, when we talk about alternating axis of symmetry, AAOS, we have to remember a few points. Okay, now what is this? It is also called as rotational reflection axis of symmetry. What it means? It is simply 360 by n rotation followed by reflection. Okay, see, rotational reflection axis of symmetry, 360 by n was simply your axis of symmetry. Okay, then followed by reflection. Now what happens in this way? If a compound is rotated 360 degree by n, then we get, if a compound, suppose I am telling this compound 1, okay, if a compound 1 is rotated 360 degree by n, then we get the compound 2, okay, using a particular axis of rotation. Now, drawing the mirror image of second, we get compound 3. If 1 and 3 are identical, then compound have AAOS. So guys, understand, if a compound is rotated 360 degree by n, suppose we are having compound 1, we rotate it by 360 degree by n, just like axis of symmetry. Okay, so we get compound 2, then we get compound 2. Okay, now by rotating we have chosen a particular axis, right, using a particular axis of rotation. Now drawing the mirror image of 2, we have got compound 2. Now we will draw the mirror image of compound 2, we get compound 3, right, we'll get another compound, that is 3. If 1 and 3 are identical, this initial and third one, if both are identical, then we can say compound have alternating axis of symmetry or alternate axis of symmetry. Now, one of the important condition here applies is that the axis of rotation you have chosen. So when we draw the mirror image of second compound, then the mirror must be placed perpendicular to the axis of rotation. Okay, here you can write note as mirror must be placed perpendicular to the axis of rotation. Okay, so if you have rotated the compound by 360 degree by n using a particular axis, let's say this particular axis, okay, then mirror must be placed here, so both are perpendicular to each other. Got it? Okay, so it is clear. So let's see by example. Suppose I am having compound 1, okay, by choosing this axis of rotation, suppose I say C2, then I get this compound 2. Okay, clear? Now as I have chosen this axis of rotation, so perpendicular to this I'll make mirror, so I'll get this compound 3. If 1 and 3 are identical, compound must have alternate axis of symmetry. Okay, clear? Now generally if a compound is having AAOS, then it will be having POS or COS or both. If any compound is having AAOS, alternate axis of symmetry, then it will be also having either plane of symmetry or center of symmetry. Now I am saying generally because there is a special case in which there is no POS or COS, but it is having AAOS. Next point, if compound is having AAOS, then it will be optically inactive. It will not show any effect to the PPL, right? Okay, so it is clear. Here we can conclude that if a compound is having POS or COS or AOS, compound will be optically inactive. So let's understand with an example. Okay, now you understand, suppose for this molecule it is trans to butene, right? Trans to butene. In this molecule, if I am taking this plane, from this plane I am rotating it to C2, means 180 degree rotation. Then I can say that after rotating 180 degree, what I will get is, after 180 degree rotation, see, using this plane I am rotating like this, this is rotated like this 180 degree, so this CS3 will come this side, H and CS3, because if it is trans it will remain trans, right? We are not rotating this part only, so again it is trans to butene, but it is rotated. Now as we see, if I have taken this part as a plane, so mirror must be kept here. This is our compound number 1, this is compound number 2, and now when we place mirror here, we can see that mirror image will be obtained like this. H will come here, CS3 here, this CS3 will come this side, and H here, this is third one. Now On observing, we find that first and third are identical. Means this compound number 1, trans 2-butene, have AAOS. Okay. So guys, note it down. It is one of the best example to show you alternate axis of symmetry. See, here I have chosen the example of sp2 hybridized using pi bond. Now I am giving you an example in 3D, 3 dimension, how to observe POS, AAOS. Okay, so let's see this one. So let's take this example. Methyl H see, this is your 1 2 3 4. It is cyclobutane having 1 2 3 4 tetramethyl. So this compound is your 1 2 3 4 tetramethyl cyclobutane. Now in this, suppose I am rotating through this 90 degree. So that will be your 90 degree rotation is your 360 degree by 4 gives you 90 degree. So it will be your S4. Sn equals to S4. Okay. What you will be getting? This is our compound number 1. Now see what you will get. See, here methyl is upside, downside, upside, downside. After rotation, suppose I am telling this is a square type, rotating like this, up will go downside. So it will be okay. So this is our second compound. If you will see, upside part has gone downside and downside has gone upside. Now, as we have chosen this part as 90 degree rotation, so obviously we can place mirror here. Okay, means I am just placing the mirror perpendicular to the axis of rotation, and what I will get is okay. So if you will observe structure number 1 with 3, you can see here it is exactly same. Means on observing structure number 1 and 3, we find that both the structures are identical. Hence 1 and 3 identical. So this compound number 1, that is 1 2 3 4 tetramethyl cyclobutane is having AAOS. Hence it will be optically inactive. Okay, so dear students, with this we are completing our axis of symmetry part, and we'll continue with next lecture. We'll continue with next lecture with next topic. Okay, see you then.